Thank you for coming. Today I'll be talking about solving crimes using Markov chain Monte Carlo to analyze previously unusable DNA evidence. A single person indicated on the left by the frowny face will end up a victim, in this case, has genotypes. The genotype is the main variable out of the hundreds of variables that we look at that's of interest for genetic identification. And people have locations on chromosomes. In the center you see a picture of a chromosome. People have two parents, and so there are two alleles, which are the values of chromosomes, and the type of markers used in forensic identification are based on the length of various short tandem repeats. These are markers that have a lot of variation in the length in an accordion-like way in the center of some random DNA. And so in this case, there might be, for a single person, there are two alleles, one for the mother, one from their father, but might be a length of 8 and a length of 12. And when that gets amplified in a polymerase chain reaction, a PCR process, what ends up happening is that you'll get peaks that correspond to those alleles. The x-axis shows the size, the y-axis shows the quantity, and that's the starting data. And for single simple source data, there are one or two alleles at a locus. Now, with crimes, typically most evidence now is mixtures. Hundreds of thousands of samples are mixtures of 2, 3, 4, 5 people. And now you have two people, a victim on top and someone else on the bottom. At the same locus, if you mix their DNA together, just because that's what happens at a crime scene, they may have up to 4 different lengths at that one locus, maybe a length of 8 and 12 from the victim, a length of 10 and 13 from this unknown person. And the result is data that no longer looks like one or two simple peaks that's easy to decipher. Instead, there's quantitative data in a pattern. In this case, we see 2 tall peaks, 2 shorter peaks. There's some other artifact peaks that come from the experiment. And patterns like this are generated at 13 genetic loci. In some kits, there can be 15 or 20 loci. This is one locus. It's called D7 on chromosome 7, and it's evidence from a murder victim's fingernails as he presumably reached out and scratched an assailant. And we'll be looking at this data for the next few minutes. To analyze this data, there is a lot going on. So at each locus, there is the genotypes, the allele pairs from each individual, that's indicated as genotype, letter G. There's a mixture weight of how much of each person, what fraction contributed, maybe 0.1 or 0.3, to the overall mix. As you can see further in the hierarchy, those mixture weights can be customized to each locus. What you're doing is you're adding together the loci to get an additive pattern that's then distorted through another 50 variables through the amplification process. And actually in our system, most of the variables end up having to be about the variants themselves, because it's how the patterns vary that make it very realistic. So the model can handle small DNA amounts. There are models for decay curves to create a DNA. It goes out to 5, 6, or 7 unknown contributors. And if you have multiple evidence, that can be combined using a joint likelihood function. If you run that model and you solve it using Markov chain Monte Carlo, one can sample from the joint posterior probability distribution. And this is just for the quantity of DNA represented as a fraction. What percent is the victim? What percent is some other person? And you can see how that chain's moving along after burn-in. Again, there's other chains happening at each experiment for is it more like 1090 or 298 as the mixture that you see in the data hierarchically. And if you were to just look at the histograms of those, now expressed on left to right, you can see how the computer can determine the relative fraction of each individual along with the variance that goes with it. Sometimes the variances can be quite broad. In this case, there's clearly about 93% of the victim and 7% of some other person, and that mixture data is now being separated into 2 contributor components. The genotype inference is more interesting. That what's happening is that patterns are being generated that add together the genotypes, which is what I'm showing here. There's a lot shown in the gray from the victim, down at the bottom. There's another person's allele pair. What the computer does is it moves those pairs all around and tries out lots of possibilities, and using actually a positive truncated multivariate normal, it compares the heights of the proposed pattern relative to the heights of the peaks, along with the variances that it's calculating. These data are count phenomena, so the variances are scaling with the heights. The amplification is actually counting up the DNA. Better explanations visually, you can see a better, like in this one, very good comparison between those colored bars and the data peaks, but the computer will consider tens of thousands of patterns, many of which, if not most of which, bear no resemblance to the data, and those will have much lower probabilities. Because it's Bayesian, we want to consider, to the extent possible, every possible genotype solution, and the approach is very objective. There's no suspect here that we're comparing with. It is all done ab initio, just looking at the data and pulling out what are the genotypes. The end result for each of these 13 locations, for each of, in this case, the two contributors, is a posterior probability distribution for each of the variables. The one of interest is the evidence genotype. There are about 100 possible allele pairs that a person can have. About 15 possible lengths, 5, 6, 7, 8, 9, 10 of what they can be. There are about 100 possible pairings. This is a very definite result because the pattern is so extreme. But objectively, a genotype is inferred from the data without looking at a comparison reference. And here, virtually all the probability happens to be put on the allele pair, the two lengths, 10 and 13, that corresponded to those very small peaks that you saw in the data. Okay, well, now that the result has been objectively inferred, a comparison can get made, and we can answer the question, how much more does the suspect match the evidence than a random person? This is a likelihood ratio. There are many ways to write out the math for a likelihood ratio. They all give the same number. There are many ways to phrase it. One way of looking at it is that it's the ratio of the probability of an evidence genotype or match divided by the probability of a coincidental genotype or match. In this case, on the left, we see that big blue bar is about 100% probability that the computer found. It's usually more diffuse, but this is a simple example. On the right is the prior population. That's what the population frequency would be of a 1013. That's around 1 or 2%. And dividing the posterior big blue bar by the prior brown bar gives a number. In this case, it's around 58. That's the likelihood ratio at this one locus. And then they're independent genetic tests. So multiplying the 13 loci together, their likelihood ratios, we can get whatever the final number is. In this case, the conclusion would be, and this is a likelihood ratio language, it's just it's not using conditional probabilities. The result would be a match between the victim's fingernails and the suspect is 189 billion times more probable than coincidence. And that's what the computer found in this case. The computer is called True Allele. And what the FBI had found from the same data, and you'll hear more about the method in a second, using a CPI method, that's an inclusion approach done by eye, is a number of 13,000. And this particular person was convicted of, based on the DNA evidence, and having a more compelling math was helpful. We've done about 200 cases at this point. Okay, so I'm going to tell you about a study that we've done. We've done about 24 validation studies, and 5 have been published. This is the most recent one. It was in PLOS ONE. It appeared this spring. It's True Allele Casework on Virginia DNA mixture evidence, computer and manual interpretation in 72 reported criminal cases. I'm going to quickly talk about sensitivity, specificity, and reproducibility. Here, I'm going to think of sensitivity more as an extent. You can also view it as an error rate. But the extent to which the interpretation identifies the correct person, in other words, true inclusions. On the 101 reported DNA matches, that we found out of 111 that were attempted on these actual cases that human review struggled with. About 82 that had a DNA statistic was over 100. This is the main plot we're going to be looking at for the rest of the talk. So what are we looking at? Here are the 101 matches that were made that determined by a positive log likelihood ratio. And there on the x-axis are numbers ranging from 3 out to 24, the number of zeros in the match statistic. The average shown in bold on the left was 11, which is 11 zeros. And you see the variance shown next to that, 5.42. It's fairly broad. So 11 zeros is an average match statistic of around 100 billion. That's what the computer found on these cases that were selected because they were difficult for people to report. The method was specific, and here by specificity, we're meaning to the extent to which the interpretation doesn't misidentify the wrong person. True exclusions without producing a false inclusion. This was done by taking these 100 or so matching genotypes and comparing them against 10,000 randomly generated genotypes that are not contributors to the mixture. It's done across 3 ethnic populations. So we have over 1 million non-matching comparisons. What we see looking at the log LR is it's overwhelmingly negative. Negative 18 is 1 over a billion billion. Okay, and also I show 0 on the right, and you see it's really not crossing 0 visibly. And if you calculate what's happening, there are a few events at log 1 or 2, and they're at a rate of like 1 in 20,000. So it's a very specific method. We're not getting the sorts of false positives at a rate of 5% that you might see with human review. The method's also reproducible. This is a Markov chain, Monte Carlo, so there's sampling variation. To what extent does interpretation give the same answer to the same question? On duplicate computer runs on these 100 matching genotypes, we can measure the log LR variation. So each point has a first score on the x-axis and a second score on the y-axis. If it were photoshopped, it would be 45 degrees, but there's actually random variation. And here, the within group variation, it was 0.3 band, 0.3 log units, which is about a factor of 2. Human variation on these sorts of on mixture methods is actually 10 orders of magnitude, studies have shown. So a factor of 2 is a little bit better than a factor of 10 billion. What does human review look like? So this is what people are doing now in crime labs. What they do is they don't really use the statistical model. They follow rules that come from Washington. I'm sure you're familiar with that. And what the rules are is that you take your quantitative data with its wonderful heights and its patterns, highs and lows, variation that can be inferred with Bayesian models, and you say, nah, let's just draw a line through it, and anything that's over the line is in, anything that's under the line is out. And so now, instead of seeing that there are 2 tall peaks, 2 short peaks, there's actually only one possibility here. That would have been the 2 low peaks would be a 10, 12. You diffuse your likelihood over 10 possibilities, and you start losing information. How much do you lose it by? This is the standard method that was used for 10 years, the combined probability of inclusion. And on the same data set, there are about 80 matches here out of the 100, and you're getting 6 zeros instead of 11, so your match statistic is in the millions. If you notice, it's now clustered. The method will basically give you the same number all the time because it's actually a random number generator. It can only give you positive values. What's the extent of inclusion? And people like it because it's simple. You add up the allele frequencies, square it, and you're done. However, the method was found to not have much reproducibility or information. So 2010, the proposal was, let's introduce a second threshold. One didn't work. We still don't like models. Let's have 2. And so this was called a stochastic threshold because, of course, you know the way you deal with a probability distribution is you draw a line through it, and then you know the truth. That was sarcasm for those of you who weren't paying attention. So now with the stochastic threshold, which I called an oxymoron in court last week, you can now throw out your data. And that's good, and it turns out you lose about a third of your information completely on a log scale, or two-thirds of information. This modified CPI shown in red is what happened on the 50 or so matches that a person could call. You see a shift to now 2 log units, a match statistic of around 140. So green was before, red is now, and the result is actually that about 100,000 DNA mixture evidence items that have been fully processed, for which nothing is being reported that can't be used for criminal justice. The computer, of course, using a reasonable model of quantitative data variation and so on, gives you the full range of information. And that's shown again on the bottom. Again, notice the means on these log curves of 6, 2, and 11. Same data, just some of it's actually analyzed. Now, this has an interesting property. If you look at a TrueAllele, the computer model, on the bottom, you'll see that it kind of looks like a uniform distribution. The reason that's interesting, especially if you read the paper, you'll see why. A uniform distribution is what you'd expect from random evidence, giving you a range from no information, 0, up to maximum information like 24, with random mixtures, which is the case here, everything in between. So we did that test. The black line is a uniform distribution, right? It's the area under the curve incrementally from left to right. And the blue line, which is TrueAllele, follows that visually. And the older green method and the newer red method of human review with 2 thresholds doesn't seem to follow a uniform distribution at all. And if you do a Kolmogorov-Smirnov test and you look at the values and the p-values, the computer model is not statistically different from the uniform model, which suggests its accuracy, whereas the human method doesn't have any such support over this ensemble of values. So we don't know exactly what the number should be. We just expect the distribution of these 100 numbers to be uniform, which the human methods are not, and the computer method is. Also in the paper, we describe the p-values, and for other correlations, and the correlation coefficient here, the R-squared value is about 10%. There's actually no correlation with information of human review. Why do we care? This is a headline from today's paper in the New York Times. It's a very big deal that hundreds of thousands of rape kits are not processed. But if you're statisticians or citizens or taxpayers or potential victims, maybe it's even more important that hundreds of thousands of evidence items are processed and then not properly interpreted and never used for criminal justice. So that's a big data problem. And the corresponding big data problem is that we have a wonderful DNA database in this country called CODIS. There's 11 million criminal profiles on it. And you need to be able to match those mixtures from rape kits and other crimes to solve cold cases and find criminals before, as in this New York Times article, people repeatedly offend over time. But the methods that are used are not statistical. They don't use probability in genotypes. They don't use likelihood ratios. It's merely association, which has a huge false positive rate. And the way the government rules solve it is that 90% of the mixture evidence is never uploaded to the FBI's database. Well, that solves the false positive problem, but it doesn't solve the fit for purpose problem, which is how do you solve crime with DNA? If you're interested in learning more about TrueAllele, we have a whole information page on our website with lots of papers, courses, videos, and we have about 50 videos of various talks on our YouTube channel. And the take-home message is, if you're going to go to the work of generating really good data, which the crime labs do, that can have an impact on public safety and criminal justice, maybe use some modern statistics, like from the last 20 years, to analyze it, to do what it is you were tasked with doing. Thank you very much.